Hello, everybody, and welcome to this lecture of the school, part of the School of Nuclei in the Cosmos in 2021. What I'm planning to do today is I will talk about isotopes in the cosmos. And this is a part of nuclei in the cosmos. I call it isotopes, and you will see in a minute why. Let me share my screen so that you can see my slides that we will be discussing. So now you can see my presentation slide, and what I'm going to do is I will teach for 2 hours in 2 sequences of 1 hour each. I will first talk about, in the first hour, about isotopes in the cosmos and about nuclear reactions and the cosmic sites that they occur in. And in the second part of the lecture, I will discuss the methods to measure cosmic isotopes and lessons learned and open questions. So let's get into this. What is the science of our conference series of nuclei in the cosmos anyway? We typically start with the table of abundances of the different elements, as it's shown here. And you see hydrogen is the most abundant element, and the total abundance dynamic range is about 12 orders of magnitude, which is huge. And beyond the most abundant elements, you see helium is already down by quite a bit. And then there is the paucity of elements for the nuclei of beryllium. And then we have intermediate mass elements, carbon, oxygen, and so forth, up to iron. And the abundances of all the heavier elements beyond iron, as you have been discussing in the last 2 days, they are about 5 or 6 orders of magnitude lower in abundance, though interesting, as you have learned. Now, this abundance distribution shows some characteristic ups and downs that are the result of physics in atomic nuclei itself and the physics that occurs in stars. And this is what we will be discussing in this lecture. How does this all start? So at the beginning, it was not so clear what drives actually the longevity of stars or the long lifetimes of stars. What is the energy source? And it was Eddington in the beginning of the last century who stated that there must be a source of energy that is of subatomic nature. That was a kind of revolutionary statement at the time, because at the time it was believed that the gravitational compression of stars would basically be the underlying energy source that would drive the luminosity of stars. And Eddington showed that the lifetime of stars would be much too short if that were the case. And so he argued that there must be another source of energy. At that time, nuclear physics was in its infancies, and so he called it simply subatomic energy. You can see that the hydrogen burning reactions in the sun are an example of such energy is released. And this is the proton chain on the left-hand side and the CNO cycle on the right-hand side. Now we know that the release of nuclear binding energy is the driving source of the energy that we have in stars. And this binding energy is shown here in the Weizsäcker mass formula, and it has a maximum around nuclei of iron, with iron 56 being the local maximum of binding energy for nucleons bound in an atomic nucleus. And the binding energy formula of von Weizsäcker distinguishes a volume term, a surface term, a Coulomb term, and an asymmetry term. So this is basically reflecting the liquid drop model of the atomic nucleus. So when we want to release binding energy, then we can either build up nuclei from hydrogen by nuclear fusion reactions, or we can do fission when we use the heaviest atomic nuclei so that we get into this maximum. Of course, the cosmic abundances started with hydrogen only, and so fission is only a possibility for the later part. But you can see that the maximum of binding energy in the iron group reflects this binding energy, and it reflects the high abundance of iron in cosmic sites compared to the other neighboring elements and isotopes. So this maximum of binding energy is reflected in our abundance distribution, and it shows nuclear physics, but somehow the reactions that produce the intermediate mass elements also must occur somewhere, and it's not everything driven by binding energy, which would be an equilibrium situation, and we would basically transform all cosmic nucleons into iron nuclei. This is not the case. As you see on this set of graphs, the primordial abundances from the Big Bang basically were only containing light elements, while today we have a rich variety that does not include just iron nuclei, but the whole range of abundances, including also the heavy elements that you have been discussing in the last 2 days. And how that happens is illustrated in this cosmic cycle of matter, as I put it up in a graph. It starts basically from stars forming out of dense molecular clouds. And these stars, they burn nuclear fuel, so fusion reactions start to occur in stars, and those occur over the entire lifetime of the stars, depending on their evolution over a million years or over many giga-years for the lowest mass stars. Once a star ends this stellar evolution, then it may eject some material either through an explosion or through powerful winds, or maybe also through dust grains that are ejected during the stellar evolution, and that returns then material from nuclear burning to the interstellar medium. When a star explodes as a supernova, this is an even more violent release of nuclear debris, and that's the way how we get the results of nuclear burning inside stars into the interstellar medium. Now, there are compact remnants like white dwarfs and neutron stars, which bury most of what has been produced in these stars, and so only a part of the ejecta get back into the interstellar medium. They then have to cool down because they are ejected at temperatures of millions of degrees. So they have to cool down to again form dense molecular clouds that then again form stars, and the whole cycle starts again. And there are gas transport processes that make the whole chemical evolution a little bit more complicated, but that's the general theme of nuclei in the cosmos. We would like to understand how this cycle of matter occurs, and we want to understand the nuclear physics aspects of this. So I will remind you a little bit about the physics of nuclei, because we were talking about elemental abundances so far. And this is the current table of chemical elements containing 118 elements. Some of those are rather short-lived, but these are the chemical elements as we know them today, sorted into Mendeleev's table, and they are sorted here by the criteria of their chemical reaction properties. These are the classification criteria, and the chemical properties of elements are driven by the valence electrons of the atomic shell, so not by the atomic nucleus itself. Now let's look at how this connects to nuclei. So when we look at a part of this table of elements, then you see that for a particular element, you can have different configurations, more than one configuration that is stable because it has different numbers of neutrons, but the same charge, so the same chemical properties, because the charge is driven by the number of protons, equivalent to the number of electrons, and those drive the chemical properties. Now, the chart of nuclei looks a little bit more complex because it shows not only the stable isotopes that are possible for each element, like for boron here or for carbon here, but it also shows the unstable ones. And this is what we call the table of atomic nuclei. And you see for 4 elements in this case, from sodium to silicon, this shows 4 rows of the table of isotopes with the stable isotopes marked in black, and the unstable ones that marked in colors, depending on their decay scheme. So we are interested in nucleons and in atomic nuclei. The atomic nuclei are the composition of configurations of nucleons, and a nucleus is a complex arrangement. Even a nucleon has probably some internal structure, and all of this is driven by the strong and weak nuclear forces, and pion exchanges among the nucleons mediate the strong interactions, and so the binding of nucleons in an atomic nucleus. All of this covers dimensions of only a few Fermi and is driven by the short range of the few femtometers of the pion exchanges that occur. It's a very strong force that is attractive in this small range and has a repulsive core at very small radii. Now, the chart of atomic nuclei as a whole contains 288 stable isotopes and probably on the order of 10,000 unstable isotopes that we don't know yet. So there's a history of discovering new isotopes, as we have seen over the last 100 years or so, and I will show you the history a little later. But let's look at the table of isotopes in a little more detail. The light elements, we have talked about protons, so hydrogen, and build-up of helium and carbon. And you see that the light element chart of nuclei is basically dominated by few stable configurations per element, 1 or 2 only, 3 in the case of oxygen. And you see that this reflects basically the stability of the alpha particle of the helium nucleus. When we go a little bit further up into the iron region, then we see that the number of stable configurations per element is getting much larger, getting up to 6 or 7, and that reflects the stability so that different combinations of nucleons can actually be stable against radioactive decay and be long-lived. When we look at the intermediate region, then we can see the effect of the alpha stability in, for example, calcium 40, argon 36, sulfur 32. So those are alpha multiples, titanium 44, chromium 48, and iron 52. So you see an effect that the alpha build-up sequence is then not dominated by stable elements anymore. The more heavy elements, they are more neutron-rich to stabilize them against the Coulomb repulsion of the protons. So that sets in already in the iron group, but at the lower and intermediate mass elements, you can still see the effect of the stability of the alpha nucleus. The heavier nuclei, then, they will have even more stable configurations, because for large numbers of nucleons, you can find more configurations that are not so different in their energy, and so they will be stable against destruction. The history of discovery of nuclei started about 100 years ago, and it really took off in the 1950s or so, with discovery of more and more nuclides as technology and nuclear technology actually was developed. The nuclear binding energy is shown here for the number of nucleons, and you see that the binding energy has this pronounced, here shown as a minimum, so it's an inverted scale here. So this is actually where we have the iron group, and for individual nuclei, you can see the multiples of alpha nuclei. They have always local maxima in binding energy compared to the other isotopes of the same element. The nuclear binding is reflected in the overall size of the nucleus. So shown here for the calcium isotopes, when you have measuring some detrended properties, so in this case the nucleus size, and you see that the nuclear size gets smaller the more nucleons you have involved, so the nuclear binding gets a little tighter. Nuclear energy levels are shown here for the example of the carbon nucleus. And you see here the ground state of nitrogen-13 and the neighboring reaction or the neighboring nucleus would be carbon-12. So the carbon-12 plus proton level would be the level that is in energy located at this point. And there you can look at transitions between neighboring nuclei. So this is the way how we illustrate nuclear reactions using the energy levels of neighboring nuclei. And in this case, you can see here how the cross-section for nuclear interactions is shown on the right-hand side. Ab-Initio nuclear models actually try to use what we know about the quantum physics of nucleon rearrangements inside nuclei. And this is shown here for different variants of the method. This is rather outdated, but it shows the principle that when you have an experimental measurement of a nuclear level, you would like to have a theory that reproduces this level structure that you can see in the experiment, measuring also the spins of the reaction. And you see that it is not so easy to reproduce that in different theories. Now, this was already some 15 years ago. So today we have a much better precision. But if you look at the scale here, then typical nuclear levels are off by on the order of MeV. So it's a substantial problem to get this right. And this is why nuclear experiments in nuclear physics still play a decisive role to learn about the properties of nuclei. It's interesting to look at the arrangements, and we have this quantization of the microscopic structure of the nucleus when we look at the Legendre decomposition in a radial and an angular part of the wave function of nucleons in the mean field of a nucleus. And then the quantization determines the energy levels that we have. Now we have a coupling between the spins of the individual nucleons and the orbital parameters that are these quantum numbers here. And this coupling in the case of a nucleus is much stronger than in the case of an atom, because in this case, it is the strong force that determines this coupling. And as a result of this much stronger coupling, we actually have a structure that is very different from atoms in that there are larger gaps developing at regions that are not so obvious compared to the atom, not dominated by the main quantum numbers. And this results in gaps, as you can see maybe here in the case of number 50, in large gaps in energy levels between different atomic configurations. And these large gaps, they are called magic numbers because they determine a threshold for further fusion or for nuclear binding, because the next nucleon that has to be bound in the nucleus has to occupy an energy level that is a substantial step above the previous ones. Now, this is determining the characteristics of nuclei, and the magic numbers, they are repeated here. Their importance actually depends on the size of the orbital effects. And so when the orbital effects in a nucleus are weakened, then these differences or these gaps between the different shells in magic numbers actually get smaller. And so the magic numbers still prevail, but they can actually change depending on coupling for nuclei that have different configurations. In the case of neutron binding, this shows the separation energy that is needed to liberate two neutrons from an atomic nucleus. In this case, one uses two neutrons to get rid of the pairing effects of the different spins. So when you separate two neutrons, then you know how neutrons how tightly neutrons would be bound in an atomic nucleus. One sees here that neutrons generally are less bound in heavier nuclei because the separation energy gets smaller. So the heavier, the larger a nucleus is, the easier it is to take off neutrons, or the more difficult it becomes to add neutrons to make heavier elements. Now, this is not the only effect. You have some shell effects that lead to kinks in the neutron binding energy, as you see here in this blue circle. And you can also see some irregularities because the shape of the nucleus as a whole can now get quite complicated. You can have cigar-like shaped or pancake-shaped nuclei, and that leads to some kinks in the neutron separation energies depending on how many neutrons you have available. All of this results then in a so-called shell quenching. So the separation between the shells, the energy differences become smaller as you have more nucleons involved. And as I told you before, it also depends on the detailed orbital parameters of the nucleus. So this will be important, or was important, as you have seen for the R process. For example, for all neutron capture nucleosynthesis, the neutron binding in nuclei is decisive. Now the table of isotopes as a whole holds this many nuclei that we don't know about. We know good information about 3,000 of those, and this is the reason why we have the heavy ion labs where we try to learn more about all the nuclei that are away from stability. They are unstable, so this is why this is called unexplored territory, and it is being explored with machines, with modern machines that are much more powerful in creating and analyzing short-lived radioactive nuclei. Now, in cosmic sites, charged particle reactions are dominant, and those actually start from hydrogen, from the light elements, and they produce basically the heavier nuclei up to the iron group. In this first arrow of nuclear reactions, that's important in all cosmic sites to produce what you have seen in the abundance distribution, namely intermediate mass elements up to iron. And there is a proton reaction sequence up here that also starts from light isotopes, and that occurs under explosive conditions where you have rapid proton capture. With rapid proton capture in unstable, very dynamic environments, you can actually get up to much heavier elements, up to tin almost. But all the other heavier elements, they are formed by either the S process that goes along the line of stability. So it's neutron capture on stable elements with always time for beta decay in between successive neutron captures. And the alternative is out here, the other extreme, where neutron captures occur much more rapid than the beta decays, so that you have a reaction path that basically is going on far away from stability and is characteristic by kinks that occur for the more stable configurations around the magic nuclei. So this is what we know from the reaction physics about nuclear reactions in cosmic sites. And now we should look at cosmic environments to find out where those reactions that I was describing will actually occur. So when we look at a cosmic site, then the reactions, they occur between particle populations. So you have one type of isotope and another type of isotope, and they may be in relative motion against each other, and you want to know the reaction rate. And that's a very different situation than you have in the laboratory, where you shoot a beam onto a target, and so you have basically known configurations and known velocity distributions, while here these particles, they are occurring in a star, so they are part of a star like our sun, and they are hot plasma, and you have to basically live with the energy distributions that are set by the temperature of the reaction partners. So in general, when we want to formulate the reaction rate, then the number of reactions divided by time and volume is shown here, and you can rewrite this. And I don't want to get into too much detail here, because you have been discussing that probably also from other talks before. But in general, you have a velocity difference here that plays a role, and the cross-section for the respective reaction. Now, when we rewrite that by figuring in that we have a Boltzmann distribution of the target and reaction partners, then we can rewrite the distribution of velocities in the volume as shown here. This is for the distribution of Maxwell-Boltzmann distribution, and for the Fermi distribution that is applicable for stellar cores of degenerate matter, we will have another distribution that we have to figure in. So trying to determine now the reaction rate, we have this product of the particle velocity and the cross-section multiplied by the density of particles, and we can evaluate that either in velocity space as written here, or in energy space by basically converting energy to velocity through just kinetic energy. And then we will get an expression for the reaction rate, sigma times velocity, which is this here. This is 8 by pi mu. That is the reduced mass of the two reaction partners. And then we have a term 1 over kT. This is the Boltzmann constant. This is the temperature. And here you find the energy of the particle, the cross-section for that energy, and the exponential factor for the Boltzmann distribution. Rewriting this, we can separate parts that are simply geometry from the parts that affect the nuclear reaction. And this reaction rate integral so contains one separated factor S that is called the astrophysical S factor, and that contains all the nuclear properties, while out here you get basically only the imprint of the temperature, so of the distributions of energy that we have, and these are normalization constants. So approximating this reaction rate integral with the astrophysical S factor can be done by making an expansion around the maximum of this term here in the exponential function, which is the sum of the kinetic energy from the temperature and the tunneling probability which you need to tunnel to get sufficient proximity of the reaction partners. And evaluating this maximum, you get a characteristic peak that is called the Gamov peak, that is now magnified in this illustration here. That's the product of the thermal distribution of the exponential Boltzmann distribution here, and the tunneling probability shown here. And the product leads to this Gamov peak, and that is the range where we need to know the nuclear reaction energies in cosmic sites, and we need to know also which typical energies we have for the different reaction sites. So looking at different cosmic environments, then this is again the illustration of the Gamov peak, and here you see that for stars and for explosions, those energies fall in ranges between, say, 10 keV and 1 MeV, which is the range shown here. For main sequence stars, you have the lowest temperatures, so the lowest energies. And for carbon burning, you get basically the hottest temperatures in the range of 1 MeV. And explosive energies can even be above that. So for supernovae, which are the most violent explosions, we run there in the situation where the Gamov peak actually is in the MeV range, and that's why explosive nucleosynthesis in supernova explosions can create many different products. This shows again the distribution of energies in stars for a low mass star and for a more massive star and for the highest mass stars. And you see those are the Maxwellian distributions that basically translate into the Gamov windows that are shown here. And I have the same graph here for some explosions at different temperatures. At explosions, temperatures are in the gigakelvin range, and you see that in this case, the Gamov peak can be extending substantially above 1 MeV. Now, we have talked about stars, but we should now get a little bit more into astrophysics and away or beyond nuclear physics. And so let's look at how a star evolves. And this is a diagram that I find quite useful because it is quite simple. It has only two variables. It shows the temperature that we have been talking about already. This is the central temperature that you find in a star. And this is the central density that you find in a star. And if you look at the case of our sun, the sun has a density on the order of 1 and a temperature of about 10–15 million degrees in its core, and it does hydrogen burning. So hydrogen burning is the start of a stellar lifetime. It is the first release of nuclear energy, and it occurs through the PP reaction and the CNO reaction if you have other elements already existing. Hydrogen burning includes weak reactions, and it releases a lot of binding energy, and that's why hydrogen burning stars are rather long-lived. But eventually, this fuel will also run out. And so when you don't have any possibility to liberate nuclear energy anymore, then in this diagram of density versus temperature, the star basically contracts. And so the line that is the diagonal line in this graph, going from here to there, basically shows the gravitational contraction as it goes on. And that is the fate of a star. And that was originally thought to be the source of the energy of the star, just contraction. So when it contracts, the core gets hotter and it gets denser. And you see here another set of dots, and that is the start of helium burning. So as soon as helium burning ignites, you again can release nuclear energy, and that basically stops the gravitational contraction again, because again, you have another source of energy that Eddington calls the subatomic energy. So gravitational contraction is essentially halted by the release of nuclear energy. And here you see the different burning stages: hydrogen burning, helium burning, carbon ignition. And here it gets a little more complicated. And here, when you have basically ignited everything so that the products are iron, like silicon, then there is no nuclear energy release anymore. So all of the stellar evolution in this diagram is rather simple. It's gravitational contraction halted by the different burning processes. And now I want to take you into a two-dimensional illustration of this, which is called the Kippenhahn diagram. This shows stellar evolution the same way as the one-dimensional diagram showed it before, but now in this diagram that basically has a time axis that starts at the birth of the star and ends at the final collapse. So it ends at where the iron core cannot release nuclear energy anymore. And you can see that this looks a little bit more complex. And the reason is that we have a logarithmic axis here. So we show logarithmic of time. And so the whole hydrogen burning sequence, which lasts 1 million years in this case, is just this part here. And the later stages that are occurring much faster, they are magnified in this diagram, and you can show the details. This is why the log scale proves so useful. So this is the time axis from birth to final collapse, and the y-axis is actually a radial axis starting from the core of the star and showing the surface at the upper end. So you can see now a two-dimensional, you can see basically the inside of the star, and the hatched regions here, they show convective regions, and the coloring shows the nuclear energy release. So again, hydrogen burning here, starts and it ends when the fuel is exhausted. Then you have helium burning, and you have carbon burning, and all the later stages. All of this happens in the core. And you see another complexity is that burning also continues in a shell. So the hydrogen burning exhausts the fuel in the core, but the envelope did not burn because it's not really hot. So the burning region actually moves further out, and it goes into a shell that is not so extended. You see, it's a little more extended initially, and then it gets rather narrow. And hydrogen shell burning, as you see here, it continues all the way through the entire life of the star till the final collapse. And the same for helium shell burning, and the same for carbon shell burning. The additional item that is important is shown here. That is the mass loss of the stellar wind. So at the surface, you are losing mass from 22 to 20 to 15 solar masses, and that's the final mass of the entire star. So it's a substantial loss in mass, but it only occurs on the outer side. So in this wind, in the stellar wind, you do not get the products of the inner burning unless you mix it somehow through convection into these outer regions. The net nuclear energy generation, as I said before, is shown here in coloring, and the net nuclear energy loss is shown in the pink coloring, and that shows that at the final stages, there is a substantial loss of energy due to neutrinos. Neutrinos escape the core of the star, and this is why the later burning stages actually are much faster. The phases of stellar evolution are pointed out here again. The main sequence is the hydrogen burning phase. The helium burning phase we call the giant phase, and all the late stages that last for a few 10,000 years. In this case, they are the pre-supernova stage, that where nuclear burning shapes the composition of the pre-supernova star at the time of its explosion. So here is a summary of the burning stages for a 20 solar mass star, listing the temperatures and the durations. And you see you start with 10 million years and you end up with a duration of just a week. Important for the stellar evolution is radiation transport. Just as a number to memorize, a photon that is produced from nuclear reactions in the core of our sun takes about 10 to the 5 years until it's made its way through scatterings to the entire surface, to the entire volume of the star, from the nuclear energy burning regions in the core to the surface where we see it as thermal radiation. So radiation transport is essential for calculating how stable a star is. And you could see that, for example, in the discussion by Amanda Caracas on the AGB stars, where radiation transport drives the instabilities that lead to mixing in the outer parts of the star. The task of radiation transport in physics is to convert radiation that has nuclear energy levels, so MeV type of energies, into thermal radiation at low energies that appears at the surface of the star. We know that our sun has a surface temperature of 6,000 Kelvin, and so that's thermal radiation at EV energies and below, and not at MeV energies. So this energy transport occurs through scatterings, through multiple scatterings, and that's an important aspect in interpreting the light that you can measure from star, or the radiation that comes from the surface. I was talking about the energy losses due to neutrinos, and this is shown here on this graph as a function of temperature. So as you go up in temperature, the energy loss due to neutrinos increases, as shown in this curve here. And you see the yellow dots, they basically mark the regions where the energy gain from burning of carbon, in this case, is equivalent to the energy loss in neutrinos. And so this shows the problem of nuclear burning at late stages of stellar evolution. You have to burn much more fuel to have enough energy that can sustain the gravitational collapse, because a lot of energy is lost to neutrinos. And this is why all those nuclear burning stages last so much shorter, because of the large energy loss to neutrinos. We have more complexities. We have, for example, stellar rotation that changes the rotational mixing. And this turns out to be quite difficult. So here are rotation properties measured for stars of different masses. And it's evident from these graphs that it's not so easy to learn about the rotation properties of stars. But we know from simulations that rotation has a strong impact on the mixing of the star. And you saw that in the Kippenhahn diagram by having here the convective envelope, and the extent of this envelope depends on the kind of convection that you have, which is modified by angular momentum transport as you have a star rotating. And you see this in a graph that shows here the different abundances inside a star as a function of the mass coordinate with and without rotation. And you see without rotation, you have very different composition lines compared to the rotational case. The gradients get much smoother, and you see the effect of rotational mixing is that the steep composition edges that you see here, for example, for carbon, they are actually smoothed out in a much smoother distribution. And that changes, of course, all the nuclear reactions that occur inside in, for example, in carbon shell burning in that case. So late burning stages in general tend to be quite complex, and the complexity is also different for different parameters of simulations. And I highlighted here interesting cases where you have a start of burning, like in this case, neon and oxygen burning at some radius that is a mass coordinate of, say, 0.4 solar masses in this case, and then the flame actually burns down to the core. So burning in the late stages does not always start in the core of the star. It may start in the shell and burn down to the core. And then you have a situation like shown here, where you have burning in the core. Here's oxygen burning, and here are oxygen burning regions in the shell that are intermittent. So you have nuclear energy releases at different radii within the star, which means that the star, of course, is unstable to convective mixing because the energy release occurs at different locations within the star. The importance of mass loss is shown here for the supernova that may eventually occur. So I showed you the mass after core helium burning here, and without mass loss, you would have a mass that is shown on this dotted line. But you see here for the red giants that have a strong mass loss that the mass of the supernova progenitor star actually turns down and is in the region of about 10 solar masses, for example, for these Wolf-Rayet stars that start out at masses of about 30 solar masses or beyond. So more massive stars that are born at a mass of 30 or more solar masses actually explode as much lower mass stars. And that determines then the type of explosion and also the remnant that you have. So for the very massive stars, if you cannot eject the envelope, then fallback may actually bury all the nucleosynthesis products in the star before it gets thrown out. And so let's look at this illustration of a core collapse a little closer. This is the onion type shell of a star as we expect it to be at late evolution. Then it forms an iron core, and that iron core must collapse under gravity. So eventually this collapse is only halted when you end up to form a proton-neutron star which is something like an atomic nucleus of large size, in this case of like 50 kilometers radius or so. So this is basically like a wall for the infalling collapse. And so a shock wave develops above this wall that is at an altitude of a radius of something like 120 kilometers. And in this region, something interesting happens, and that's why I expanded it here a little bit. The infalling material comes from above. These are iron nuclei, and those iron nuclei, they are basically decomposed into alpha particles and free nucleons as they hit this shock, because the proton-neutron star emits very high intensity of neutrinos as it forms neutrons from protons through inverse beta decays, through basically neutralization of the matter. And this neutrino intensity leads to a decomposition into free nucleons. And as this whole region is unstable and will eventually explode, these free nucleons then can recombine into nuclei that are then again more stable. And this readily forms iron group nuclei, in this case, nickel 56, at a radius that separates the compact remnant from the ejecta. And nickel 56 is the product that is most stable from the matter that has been decomposed. And nickel 56 is also radioactive and makes a supernova thus shine very brightly. And this is why we see core collapse supernovae as bright events, because all the matter is basically reassembled into matter that is most stable, so iron group nuclei predominantly. Now this collapse is shown in a very simplified scheme here, and actually a little bit more complexity can be seen in this two-dimensional representation down here, where you see that downflows and upflows actually can occur simultaneously. So it's not a homogeneous collapse as we always imagined. It's actually something that is quite a bit more complex in its dynamics. And we must say we don't have a full model of how that happens. So, for example, we don't know if the collapse will actually form a black hole directly, or if it if it will be successful to create an explosion. And that is what we have learned in the past 10 years or so, that as a function of mass, there are some regions where you form directly compact remnants like black holes. And then there are other regions that are even at higher masses where the black hole collapse does not succeed, and you actually have an explosion again. And that explosion can return nuclei back into the cosmic cycle of matter, and is thus key to chemical evolution. And you see that these islands of explodability, as they are also called, they are not so well determined. They are calculated in these models, but it's not so clear how much realism do we have in these models, and we need to confront these with observations. Core collapses are complex, and they are involving also magnetic fields, and so it's not clear what is actually the start of a supernova explosion. We basically believe now, and we know that with observational support, that the neutrinos that I mentioned before from the proto-neutron star, they are decisive in launching the explosion, because they deposit energy in the surroundings of the infalling matter that is capable of lifting off and throwing out the entire envelope. That is a key mechanism that is probably pretty sure. But then magnetic fields may play a role as they are winding up with the collapse, and that may add another source of energy. So actually explosions may be more like jet-like, because the magnetic fields immediately imprint a preferred axis along the magnetic pole of the collapsing star, and that leads to differences in the equatorial versus the polar regions of the collapsing star. Not clear how important this explosion physics is in particular explosions, and we can only say that one star may explode a little different than another star explodes. And that has also been seen in simulations. So simulations have shown that successful explosions occur, in this case, when you see here the trajectory launching off. So this is a two-dimensional diagram with a time axis showing here about 300 milliseconds on time. And you see that successful explosions occur, but not always. Here in this case, the 25 solar mass star does not explode, while 27 and 15 solar mass stars do explode. So this is an illustration of those islands of explodability, which, however, also apparently depend on the details of the simulation, like if it's carried out in 2 or 3 dimensions. And these simulations are very expensive, so one cannot run all the cases of all the parameters in 3-dimensional models. And this is why we have quite some uncertainty left here. Finally, we have to come to the compositional evolution, because we want to understand nuclei in the cosmos as a whole. And so we have to look at the gas flows and of the way how gas is incorporated in stars and finally burned. And when we do that, we trace first the gas flows in terms of the conversion from gas to stars, and that involves the star formation rate and the rate of mass ejection. And the question is then, when is the mass ejected from the star? This occurs with a delay that reflects stellar evolution, because the star has to first form and go through the evolution that I described. Eventually, it will explode and return its products in terms of the yield. And the newly contributed ashes, they are then composed of the elements and isotopes that we would like to understand from the nuclear reactions. So we have to basically not only look at the mass, but we look at the particular isotope that we are interested in and find out how much of a particular isotope is ejected at some point after star formation into the interstellar medium. This is how the modeling of compositional evolution works, and it has to basically calculate the yields of a particular isotope for each of the sources that we know. And now we have different sources. We have the stars, we have the core collapse supernovae, we have the type 1 supernovae that occur in binary systems, and we have more such sources like neutron star mergers. So for each of those sources, we have to find the right parameters for their stellar evolution and for their efficiency in ejecting a particular isotope. And all of this sounds pretty complicated, and so it may be surprising that in your basic lectures, you always get confronted with this here, with how do we understand the origin of elements. And it seems like everything seems understood, because people make color marks here and say iron peak elements mostly come from type 1 supernovae, and the intermediate mass elements mostly come from type 2 supernovae. And you heard about the R and S process and the origins in S process elements in massive stars and AGB stars, and R process elements in maybe neutron star mergers. So this is an older graph before we knew about neutron star mergers. Anyway, going back to the elemental abundances, the story almost looks like it would be solved. But we have seen now that elements are only half of the story, and actually all the nuclear physics acts in this chart of isotopes or of nuclei. So it will be important to understand how isotopes are converted into each other, and eventually, and that's what I will talk in the second hour, how to measure this, how to make measurements of particular isotopes in the cosmos, in the interstellar medium, and also in particular sources, if we can. You may think that this is solved, but this is an illustration which shows that chemical evolution is actually not solved. This is one of the latest detailed publications that confronts observations of particular elemental abundances, like in this case magnesium, with the modeling. And you see the red line here. The red line is the model that seems to represent the observations of abundances of magnesium in star. manganese in stars quite well. But you see that for cobalt, which is not too far away in the chart of nuclei, the theory apparently cannot reproduce the observed abundances. The trend in global is well reproduced, but if between manganese and cobalt, you see a discrepancy. And for lighter elements, you see that in the case of nitrogen, there is a big question of how we explain the early enrichments that was observed. Theory apparently doesn't reproduce that. So there is still work to be done. And there are inconsistencies also with the event rates that are put into such a model and the observed event rates. So for example, the number of supernovae that we need for making this chemical evolution is inconsistent with the number or the rate of observed supernovae. And then there are unclear impacts from rare sources, especially for the early metal-poor universe, where the observations show the green data points. And you can see here a simulation or a calculation with different delay times between formation of the system and release of its ejecta. And you see that the abundances in the early universe would be, or in the early galaxy, would be very different depending on the different delay time assumptions. And finally, we have learned from Gaia also that there are stellar streams that show that our galaxy actually has been mixed, has been colliding with other galaxies. So we have to be a little careful when we take stellar abundances as observed and put into these graphs. They may actually come from environment that is another galaxy that is thus not really related to the star-forming environment that we have been assuming for our own galaxy. And all of this adds complexities to the modeling. So I think this illustrates that it's far from being solved. And we would like to talk in the second hour then how different messengers from those cosmic nucleosynthesis can actually be exploited to learn about the complexities of nuclear processes. As shown here, the nuclear reactions, they are complex. They are proton captures, neutron captures, alpha captures, and all of these are very complex reaction paths, especially in the intermediate mass range for carbon and neon shell burning. And these reaction paths, they will be quite different for explosive burning. And it's even more uncertain for the environments of between S and R process, because the irradiation with neutrons making the heavy elements is probably a very dynamic environment in sources like neutron star mergers, which are quite dynamic. And therefore, we need to compose our measurements and see how much we can learn about these individual elements and how they create specific isotopes. And this is what we will be discussing in the second hour when we talk about how to measure nuclei in cosmic sites and how we learn from them. And with this, let me close for this. And now you can have a break and digest what I have been talking about. So we will continue this lecture with the second hour soon.